Hi, my name is Wei Hu, and I'm here today to talk to you about some of the new developments around Kubernetes and microservices with the Oracle database. I have a love-hate relationship with Kubernetes. I think it's great technology, but it's still too hard. According to a survey, 77% of organizations cite Kubernetes as a central part of their digital strategy. Kubernetes is becoming the standard for deploying containers in production, and developers are embracing it for both new and existing applications. Many microservices applications are deployed in containers managed by Kubernetes, and I think that's great. But you get comments like, guess what? Kubernetes in production is hard. In this talk, we describe how Oracle is embracing and innovating in the space to make it easy for you to deploy enterprise-class applications on this technology. I want to start by talking about containerized images. Okay. First, Oracle Database 19c is fully supported in Docker containers. We're releasing Docker container images for Oracle Database. That's for Enterprise Edition, SE2, Single Instance, Rack, and Sharding. And these images are available at our container registry. These images are supported for production use. I think that's really important. Okay. Now, Rack is special. Rack is supported only for on-premises deployments. For cloud deployments, we recommend the use of our managed cloud services, such as Autonomous Database, Exadata Cloud Service, and so forth. And of course, when you use these Rack images, they are supported assuming that the underlying operating system hardware and so forth are also supported for Rack. The images that we release can be further patched and used as customized code images. Okay. We release Docker images for base releases. Furthermore, we publish the Docker files that we use to create these images on GitHub. And so you, our customers, can take the same Docker files and scripts that we use to build our images, to build your own customized code images that contain one-offs and so forth. The images that we provide, and the ones you customize, can be deployed in Kubernetes. And they can be deployed in Kubernetes using Helm charts. Charts basically describes the application structure so that Helm can install and configure the pieces of the application. For example, for Rack and Sharding, where there are many moving pieces, this is very, very helpful. So this command here, for instance, installs your Oracle database in Kubernetes cluster in a default configuration. We publish the Helm charts for the Oracle database on GitHub also. And the idea is that we want to make it possible for you to create and extend the tools that we use to create and provision the images. There are many Kubernetes distributions out there. Okay, so the question becomes, how do we test? What do we support and so forth? Well, the first thing is that our container images are built against standard interfaces. Then we test and certify them on the Oracle OLCNE, which is Oracle Linux container interface, which is OLCNE is a CNCF certified Kubernetes distribution. We also support these images on Red Hat OpenShift, because we hear from you, our customers, that that is a very popular distribution. So Red Hat OpenShift uses the same standard interface that we do. Okay? But we will further do some sanity checks with the same Red Hat OpenShift releases as we do for the Oracle Linux releases. Providing supported Oracle database images and Kubernetes is an important first step. Okay. But we want to go further. We want to make the Oracle database natively part of the Kubernetes infrastructure. That means you can start, stop, monitor, patch, upgrade, and perform other lifecycle management operations from Kubernetes. And we want to make sure these capabilities work whether the Oracle database is deployed in the cloud, on premises, inside a Kubernetes cluster, or even outside of Kubernetes. To do this, we do two things. First, we are making the Oracle database natively observable in Kubernetes. And secondly, we're providing the Kubernetes operator for Oracle database. Native observability. One of the things that I really love about Oracle is a set of rich performance and runtime statistics, so you can really find out what's going on and so forth. We're making this data accessible by popular open source frameworks that are also used with Kubernetes. So, for instance, we're building extensions to Prometheus. These extensions are called exporters to publish database metrics. We're developing best practices for using Loki to monitor and aggregate activity from the application to the data tier. We are providing Grafana dashboards to display this data. And so on the screen here, you see two screenshots from the current version of the Grafana dashboards. And we want to support Oracle databases deployed within and outside of Kubernetes. And this is important because these open source tools are actually very general and can be used in many environments, and we want to support them. And our goal is really to make it possible for you to monitor and trace the entire application end to end using native Kubernetes tools and dashboards. And all these scripts and tools I talked about are available on GitHub. Observability is the first step. The next step is really the Kubernetes operator. Operators are extensions to Kubernetes to manage applications. They allow you to use the Kubernetes command line, the kubectl, to manage the life cycle of an Oracle database. For example, here, this one-line command allows kubectl to provision an autonomous database. As you can see from the command, the Oracle database being managed by the operator can be anywhere. It can be running inside a Kubernetes cluster or outside of Kubernetes. It can be running on-premises or in the cloud. It can be running in the same or different cloud or hybrid cloud configuration. The way we do this is by providing multiple operator backends for this common database operator, and these backends are called controllers. And our goal is to make the Oracle database deployed anywhere, natively manageable by Kubernetes. Let me show you how this works. You have somebody running the kubectl command. It interfaces to the database, Oracle database operator running inside the Kubernetes cluster. The operator has three different controller backends. One controller talks to Oracle databases running inside containers deployed within the Kubernetes cluster. Another controller can talk to an autonomous database running the Oracle cloud. And the third controller talks to an on-premises databases running outside of these on-premises databases that are not containerized, running outside of the Kubernetes cluster. And what's interesting is that they all interface to the common Oracle database operator. And the lifecycle operations that we are supporting are things like provisioning, binding, start, stop, terminate, backup, restore, scaling, patching, upgrade, and so forth. Now, I made a big point about how our operators will manage Oracle database running on-premises as well as in the cloud. And I think that's really important. We believe that the Exadata and the autonomous database service are really the ultimate in simplicity. Okay? So rather than the operators allow you to manage databases from within Kubernetes, but isn't it much better if the database was self-managing? Okay? That's why I say for the ultimate simplicity, use Oracle's cloud services. And you can deploy a full database as a service model using the Exadata database service, which runs on the world's best database platform, which is Exadata. And we automate and optimizes all database infrastructure from the hardware up. And we provide user-controlled database automation, elastic scaling, pay-per-use. And this technology can be deployed in the public cloud or in your data center with a cloud and customer model. I would like to review the Oracle database Kubernetes operator roadmap. We're releasing the functionality in stages. Right? Available immediately is support for the autonomous database shared, single instance containerized databases running Enterprise Edition, SE2, and XE, as well as sharded database where shards are containerized also. Then over the next 12 months, we'll be releasing support for additional configurations of autonomous database, such as autonomous database dedicated, ADW, autonomous JSON database, Apex, VMDB, EBCS, and then rack containerized databases, as well as on-prem databases, including Exadata. Our plan is to test on major Kubernetes distributions as well as third-party clouds. So please give us your input in terms of what is most important for you. And you can learn more about this in this session on the Kubernetes operator. We're really fully supporting our Kubernetes, and we're fully embracing the use of containers in Kubernetes. First, by supporting container images in production on both Oracle and non-Oracle infrastructure. We're providing Helm charts for configuring these images in Kubernetes. We're providing adapters for Kubernetes open source observability and tracing frameworks, as well as operators to allow Kubernetes to manage Oracle databases. And all of this is open source, available on GitHub. Next, I want to talk about what we're doing beyond this to innovate, to extend containers in Kubernetes to support high-end OLTP. The challenge really is, how do you support mission-critical microservices? Here's a quote from the CEO of Volterra. Even though Kubernetes has become a red-hot trend among tech media and influencers, few organizations are actually deploying Kubernetes for critical business applications. I think there are two reasons for this. Number one, the technology is still fairly complex. But secondly, there is some support that is currently missing. If you look around today, real-time, high-throughput OLTP applications use transaction monitors. Things like Oracle Tuxedo and IBM CICS. Okay. This is what things like money transfers, credit cards, reservation systems, etc. use. And microservices applications that want to deliver the same level of performance and reliability need similar capabilities. And that is what we're working on. We're actually working on this thing called the Transaction Manager for Microservices. It provides distributed transaction support for applications deployed in Kubernetes. First, we will provide strong consistency with XA and try-confirm cancel transactions. Then, we also provide eventual consistency with Saga orchestration. We'll support popular programming languages and frameworks: Java, JavaScript, C, C++, Golang, Python, and Apex. And the key part is that all this will be deployed and managed as a native Kubernetes service. It will be integrated with the Istio service mesh. It will be integrated with the native logging, monitoring, tracing facilities. So it would just look like it's just a natively part of Kubernetes. Okay, at this point, I sort of want to step back and look at microservices architectures as a whole. This will sound familiar. Microservices are attractive but hard, and the journey is replete with failures. Here's a quote from the CTO of Perform Software. Expect to see more microservices failures as teams continue to struggle with it in 2021. And here are various quotes about why microservice projects fail and so forth. I think failure is interesting, but far more interesting is success. Okay? I believe that to be successful with this technology, you need two things. Number one, use the best tools available. And that's the Oracle database. Okay. And secondly, follow proven architectural patterns. Okay. Do things that have been proven to work. Let me start with the best tools. The Oracle database, supports multi-tenant for microservices. And this really is based on containers. Containers simplify deployment by enabling rapid and lightweight deployment of logical systems instead of physical systems. And Oracle has implemented the container concept natively in the database. This means you can deploy lightweight, pluggable container databases. And that's much better than deploying and managing physical databases for each microservice. What it means is that many pluggable databases can be deployed on a single physical database, and that simplifies operations. And pluggable databases can be easily cloned and moved between physical databases. I'm happy to announce that with 21C, Oracle Database XE Edition now supports unlimited pluggable databases because we want to promote and make it easy for customers to adopt this technology. The multi-tenant is the first part. The other part that is very important is Oracle Database's support for transactional events. Events is sort of key to how microservices work together. The Oracle Transactional Event Queue, TEQ, is a free event platform built into the Oracle database for 20 years and has been continuously enhanced. Previously, it was called AQ, or Advanced Queuing. TEQ makes developing microservices simpler because publishing and consumption of events is transaction integrated with data changes. And we handle difficult cases like events that change database state and produce more events. It provides exactly one semantics without expensive two-phase commit and worrying about idempotency issues. And we provide security, backup, recovery, and so forth for both events data together. So it's all consistent. TEQ has a scaled architecture that handles over 1 billion events per second. And TEQ implements transactional cross-database event propagation without relying on two-phase commit. And for interoperability, we use the Confluent source sync connectors to enable events to be shipped between Kafka and TEQ. TEQ is in production used by tens of thousands of enterprises. And you get more details about how TEQ works and how in the database, at this session, transaction event uses Oracle TEQ in database, interoperating with Apache Kafka. So beyond great technology, I want to talk about patterns. I strongly believe that the key to success with microservices is to use proven architecture patterns. And the Oracle database simplifies 5 key microservices patterns. And they are the transactional outbox, the idempotent consumers, event sourcing, command query responsibility segregation, sagas, and long-running actions. First, the transactional outbox. The transactional outbox is a pattern where you write data into a table and publish an event as a single transaction. Traditionally, this is a very complicated pattern because it involves a lot of application code to ensure that the update and event publish are atomic. Transaction event queues simplify this pattern by atomically persisting the DML of the event. Okay. So what it means is that you can do a database operation and publish an event as a single operation. We maintain total ordering within each event stream and recovers for any kind of failure, same as database recovery. And we provide exactly once delivery events. By making this transaction outbox a built-in pattern, it makes application code simple. And to show you how simple it is, here's an example. We'll try to draw what this pattern is with and without TEQ support. On the left-hand side is heterogeneous architecture, whereby you use an external event platform like Apache, and you have 2 microservices, the order service and the inventory service, and they're working against 2 databases. Okay. And you see the bubbles in brown are sort of the code that you had in the application we had to write to handle these cases, to create the idempotent producer, to do the update and produce event detect failures and handle duplicates and so forth. Okay. On the right-hand side is what it looks like with Converged Oracle database with the built-in TEQ. It's building transaction outbox and exactly once event delivery. You can notice that all this code is gone. Okay. So not having code is great. Number 1 is less work to do. And number 2 is having no code means there's no bugs. Okay. So I think this picture sort of graphically shows you the simplification that can occur when this kind of technology is built into the event system. And we have a hands-on lab that shows you how to actually build these applications and compare them for yourself. And they're available at this microservices landing page. And the lab is called Simplifying Microservices with Converged Oracle Database. Next, I want to talk about idempotent consumers. In real systems, events can be lost or duplicated due to crashes, network partitions, and so forth. To handle this, event consumers must be idempotent. This means you have to detect and ignore duplicate events. For example, if I get an event to say withdraw $5,000, it is very important that I do it only once and not 2 or 3 times. The Oracle Converged database simplifies idempotent consumer pattern by supporting strong exactly once event delivery. This handles crashes, network failures, point-in-time recovery, failing over disaster recovery site. It's easy to use and does not require distributed two-phase commit. By comparison, some other event systems, claim to have at most one semantics. However, they don't work when the producer session crashes. Okay, and they require extra consumer code, application code, to externally persist event offsets. So it doesn't work, and it's harder to use. Okay. The nice thing about the pattern that we produce is that with Oracle TEQ, consumers do not need to do deduplication. Okay, so you basically don't even need to implement idempotent consumers pattern. Next, I want to talk about event sourcing. But before I do that, I want to review some of the key concepts. The Oracle database supports both application-coded events and data events. So far, the type of events I'm talking about, the ones that support transaction event queues, are what are called application-coded events. They're called application-coded events because they require application logic to create, to generate, and to interpret and act on the events. There's a second type of event called data events. Data events are state changes that are published to keep data synchronized. Okay. So for example, price change is an example of a data change. Data events, unlike coded events, can, in fact, should be handled automatically. Because you can do it automatically, you can avoid expensive error-prone hand coding of state change capture, where you did it wrong and lead to data inconsistency. Okay. Because imagine you have to write logic actually to monitor when data changed, transform the data, send it, and so forth. Okay. And this can be done automatically. In fact, the Oracle Golden Gate automatically captures, transforms, and publishes data events to hundreds of target types. We support all the major databases, storage types, and so forth. And the nice thing about Golden Gate is that the entire process is automated, runs in parallel, and it's transactional. So this gives you both high performance and great consistency. This makes Oracle Golden Gate the ideal infrastructure for developing what's called a data mesh. And to go into these concepts in greater detail, please review this session called Rethink Database Architecture to Embrace Modern App Dev. So now, with that introduction out of the way, we can talk the pattern itself, event sourcing. Event sourcing is a pattern where operations are stored as a sequence of events. Events are recorded in the event store and can be replayed to recreate data for new sessions. The Oracle database simplifies event sourcing for microservices by supporting both application-coded events and data events. For coded events, we recommend use transaction event queues with Oracle database to benefit from transactional consistency. And if you need to go between Oracle, TEQ, and Kafka systems, you can use Kafka connectors to transfer coded events between Oracle, TEQ, and Kafka. Then you go to heterogeneous systems and services. For data events, use Golden Gate to publish and consume data in real time. Okay. And you can run Golden Gate between microservices, between different applications, between different clouds to enable multi-cloud. And you can use Golden Gate to send data events between operation and analytic systems. And this last point is actually very important for enabling the next pattern that I talk about, which is command query responsive segregation, CQRS. This is a model where you use separate databases or models or commands, which are transactions, OLTP transactions, writes, as queries, which is analytics. And the idea is this way allows you to independently scale either the OLTP workload or the analytic workload. Oracle's native support for data events simplified the CQRS pattern. Number one is you can use separate PDBs for writes versus reads. So for example, you can use ATP for transactions and ADW for analytics. Next, you can use Golden Gate as a data mesh to create and maintain the replicas for analytics and reads. And this makes it simple, high performance, and consistent. And I wanted to remind people that Golden Gate is the market and technology leader for data events and replication. It is trusted, used, and trusted by thousands of enterprises, including 80% of the global Fortune 100. The last pattern I want to talk about is really sagas in the database, and this is something that's coming. Sagas are a distributed transaction protocol for data consistency across multiple microservices. And Oracle is working on simplifying the saga pattern by implementing it in the database. Okay. And our goal is really to reduce code complexity. By some of our early findings, we can reduce 80% of the code that's required to implement sagas in terms of the compensation logic and so forth. So stay tuned. There'll be more developments in the space and we'll be talking to you about. Now I'd like to summarize by talking about our microservices and Kubernetes platform. First, you can see up here, we are planning to support, the popular programming languages, right? And we're building transaction management support such that we can support high-end OLTP. We're integrating our technology with the observability infrastructure, typically running Kubernetes, things like Grafana, Prometheus, and so forth. We're making our databases natively manageable by providing database operators for the Oracle database. We support microservices running inside the containers. We support databases running inside the containers, or databases not running inside the containers. Right? But what's interesting is that with the use of database operators, whether they're running within the container, whether they're running within Kubernetes or not, it doesn't matter. It looks the same to Kubernetes. Then, in terms of the database itself, we support multi-tenant so that we give you native containerization built in the database, as well as native event platform. We support, for coded event, we support TEQ, transaction event queues, and for data event, we support Oracle Golden Gate. And this whole infrastructure, we believe, is a wonderful platform for deploying, running Kubernetes and microservices applications. And this link here is our microservices landing site where you can go to find more information. I would like to wrap up by showing you some other on-demand sessions that you may find interesting. There's a session on transaction event queues, the session on the database Kubernetes operator, then there's a session on application workflows with ZQ messaging. Finally, I want to remind you that there's a hands-on lab where you can actually try and play with this technology yourself and decide for yourself and how good it is. Okay. With that, I want to thank you for your time and hope you have a good rest of the day.